Hello all, welcome to the AI driven perception learning and mapping for drones course. So the learning objectives of this are essentially we will go over a single neuron model and perceptron models. Essentially we will try to see their effects in MATLAB. Essentially we will try to define certain types of input, see how does the error surface look, and then try to use it for various problems. So let us say we use it for a 2 class problem or a 4 class problem. What are the perceptron models that we have used and what is their interpretation, how does the decision boundary look, etc. So let us start with a simple neuron model. So essentially we have a neuron which has 2 inputs, which is x1, x2, their corresponding weights, biases, and then the output. Right. Now this is essentially the representation of a single neuron. So we have inputs which is input 1, 2, which is also highlighted by x1, x2, their corresponding weights w1, w2, the bias weights, right. Essentially all of this is passed to the neuron. So we have w1 into x1 plus w2 into x2 plus b. This whole operation is then passed through an activation function. The output y is essentially highlighted as an activation. Output y is essentially highlighted as y is equals to f of w1 into x1 plus w2 into x2 plus b. In the last tutorial we also observed certain importance of either the slope in the linear regression model, but we also understood the effects of the bias term b. We saw how it pushes the decision boundary, and hence it is essentially very important when we are trying to understand the decision boundary of the perceptron model. Now let us go over the basic definition for the neuron parameters. So let us define the weights w1, w2, which is essentially highlighted here. Let us also define the value of bias, which is kept at as minus 1.7. Let us define the transfer function or the activation function as any of these activation functions. So let us take a hyperbolic tangent as the activation function for now. We observe that we have an input. This input is passed through the weights w, and along with bias this is essentially passed through an activation function resulting in the output, right. This is something similar to the representation we just saw earlier, but MATLAB has its own specific representation, right. Now one important part is if we keep varying the value of x1 and x2, we can essentially have varying outputs, right, and for varying values of x1 and x2 we can pass it through f eval f comma activation potential, right. Okay. Now essentially when we plot the output of neurons for a varying value of x1 and x2, we observe the curve on the right. So with varying x1 and x2 they would have a corresponding value of the output, and we can see it in a 3D plot. So this is how the plot would look with respect to an output. Okay. Again, we will not in detail go over the syntax of MATLAB. However, when we say x1 comma x2, it is essentially a grid ranging from minus 10 to 10 with a step size of 0.25, right. So this is how the plot works for the x and y axis, and for various values of x and 1 we plot the outputs. Now this is essentially a construction of a neuron using a specific toolbox from MATLAB. So in this particular MLX file we first define the network, which is essentially a linear layer. Once we have a linear layer we configure or initialize the network. Finally we define the activation function, the weights and biases, and then we generate a corresponding plot. This plot is essentially the plot that we had discussed earlier, which is the representation of the neuron. Okay. Now let us go to a different example and let us try to see the effects of a single layer feed forward network and a multi-layer feed forward network. For this particular tutorial, we will skip the RNN part, which would be covered later on. Okay. Let us define the input first. The input is defined as a vector of 1 to 3 elements, and essentially the transpose of it is highlighted here, right. This is something we saw even in the first lecture of basics of math, where it is important to define a vector, and once we have defined the vector, it is then passed on to the neuron model. We also defined its corresponding output, which is essentially the target. Now let us take a look at the feed forward single layer feed forward neural network, right. Now essentially it has a different way of initializing or creating the network and then defining the activation function. We will not go in detail about this syntax because the syntax is specific to MATLAB. For Python, using PyTorch and TensorFlow frameworks, it is slightly different. However, we do understand what are important while defining a single layer feed forward network, right. It is important to define the number of inputs that it would have. It is important to define the number of layers that it would have. So, number of hidden layers. Do we need a bias connection? If yes, we will put it as tick, right. Let us assume that we want the layers to be connected. So, currently we only have layer 0. Do we want the layer 0 to be connected to itself? No. So, we will put it as 0 here and so on, right. We can define the transfer function here, which is given as tan of sigmoid. We can define the transfer function here, which is essentially given by line 15 and 16, and once we have all of these parameters defined, we can then configure our network. The network looks something as observed on the right. So, there is an input, essentially the number of inputs required to train the model. We have weights corresponding bias, and we pass it through an activation function. Now similarly, we can also have its variant in the multi-layer format. So, multi-layer feed forward network is essentially highlighted here. The syntax more or less remains the same. So, it is number of inputs, number of layers, do we need a bias connection, and then the layer connection essentially is the layer 0, the connection between layer 0, layer 1. So, what are the weights, how are those weights initialized? What are the number of hidden neurons in corresponding layers, and what are the transfer functions? Once we have defined this, we would define essentially the network, which consists of essentially the net, the input and the output, right. Now this particular thing is described in the block diagram on the right. So, we can see that there is an input. The input is passed through layer 0, which has weights, biases and the activation function, which is then passed into layer 1. Finally, after the activation function of layer 1, we have the output. Okay. Now let us since we have defined these particular single layer and multi-layer feed forward networks, let us maybe take an example and see their behavior, right. So, let us perform a classification of linear separable data using a perceptron model. Now compared to the examples we have seen in our lecture, essentially we want to have two clusters of data which is belonging essentially to two classes, and we want to have a decision boundary that separates both of these data. We will try to do that with a perceptron. So let us define an input and its corresponding output. Now essentially in this particular piece, in this particular code, let's define the input and the output, right. So let us define the 2-dimensional data and try to see how it is visualized. So let us take the number of samples as 50 per class. Let us keep the offset from the class as 5. Let us define these classes given as x1, x2, and for both of these classes let us define the outputs y, right. And once we plot it, we can observe that this is how the classes look. So we have vectors to be classified. We have class 1 which is represented here, and we have class 2 which is represented on the above part of the curve. Now let us essentially train a perceptron model. When we train the perceptron model, it essentially has various variants like epochs, what is the time taken to train this particular model, etc. Now essentially we will go into detail about training of perceptron maybe in the next tutorial. However, let us see the influence. Let us see the influence of the decision boundary. So let us plot the decision boundary, right. Essentially we want to observe the decision boundary of the perceptron and see how it divides these two classes. Sometimes the decision boundary is not optimal. If the classes are linearly separable, they will essentially converge. We saw an example where the decision boundary did not work in the case of an XOR gate. However, it worked for other types of Boolean operations, right. So let us observe this decision boundary. We have classes C1 and C2. From C1 and C2 we can essentially, the perceptron which we had initialized above tries to draw a decision boundary like this, trying to classify both the classes C1 and C2, right. Now let us take an example which is slightly more complicated. So let us perform the classification of a 4-class problem with the perceptron network, right. Now this is different from the earlier example we saw, because it has 2 input, it has 2 outputs, and it has 4 categories, right. So there are essentially 4 clusters belonging to 4 categories in the 2D space. Now similar to the MLX file we saw earlier, we essentially have the number of classes as 30, the offset is given as 0.6, we have 4 of these classes defined, which is A, B, C, D, essentially having a random initialization. However, with an influence of the offset, if we see the offsets influence, we can actually see that all of them would be in certain clusters, right. Once we have this, we plot all of these points. Now this is represented in the curve on the right. So we can observe that we have class A on the top, we then have class B, we then have class C, and at the end we have class D, right. Now our goal is to clearly come up with decision boundaries that clearly divide these classes so that we have separate clusters. Now similar to all of these input data, we have their corresponding outputs defined. So A is given as the encoding 01, B is given an encoding 11, C is given an encoding 10, and D is given an encoding 00. Now let us create a perceptron model. Now essentially we do understand intuitively how the perceptron model would look like if it had 2 outputs, right. So this is how essentially the perceptron model looks like. So this is essentially just a very simple extension of the perceptron model we saw earlier. So we have an input, we have in the perceptron model itself we have the weights, the biases, which is then passed to the activation function. At the end our y is 2. So, our number of outputs in this case is 2, right. So, it is just a very simple extension of the previous perceptron model we saw. However, in this case we have 2 outputs, that is the major difference. Now, we perform a training operation here, again not focusing more on the syntax part of it, but let us just go over it intuitively. We define or initialize the value of an error, right. We try to go over the iterative loop, which is essentially to minimize this error or to stop within 100 iterations. The value of n is initialized, and for each iterations it keeps getting added with 1. So, n is equals to n plus 1. We have net ye, which is kept as adapt of net pe. Adapt is essentially updating the perceptron model. Once the model is updated, we have a corresponding output value, we have corresponding value of the predictions, and we have the error, right, and we just keep plotting all of this on the curve. Now, once the model converges, we actually see that the perceptron has this kind of a decision boundary. Now, since it has 2 outputs, it can have 2 separate decision boundaries. One boundary is highlighted with the blue part, with the blue line, the second boundary is highlighted by the red line, right, and essentially it divides this particular plane into 4 quadrants, with each quadrant with its specific class, which then calculates the output y. The output is decoded according to the color scheme into one of these classes. So, as observed here, the value of p is minus 0.27 and minus 0.3. We can plot it in this particular part of the curve, and if we do that, we can essentially identify which class it would be, right, and this is a dynamic process. So, if I keep the value of p2 as 0.61, when we run the whole MLX file, it first defines the network. Once it defines the network, it will try to categorize the point here. So, the value of p is minus 0.27 and 0.61, which is this part, and hence it classifies it as the class A, right. So, the input p is now classified into one of the clusters. The cluster in this particular case is class A. To summarize this particular tutorial, we went over 2 fundamental concepts. We went over a single layer neuron where we defined the parameters, and we also saw how after a quick training it could be used to generate a decision boundary to define or to separate 2 classes, which is C1 and C2, and we extended this into a 4 class decision boundary problem where we had 4 classes. We trained a perceptron with 2 outputs, which essentially generated 2 decision boundaries. It was used to cluster class A, B, C, D, and hence we saw how a 4 class linearly separable problem could be solved using a single layer perceptron with 2 outputs. Thank you.